Hello, it's time for another homework tutorial. This time we're going to be working on capital budgeting methods, net present value, internal rate of return. Let's jump into the Excel file. Problem 10.9, it says the Bedford Falls Bridge Building Company is considering the purchase of a new crane. George Bailey, the new manager, has had some past management experience while he was the chief financial officer of the local savings and loan. The cost of the crane is $17,291.42. That's going to be our outflow, minus $17,291.42. And the expected incremental cash flows are $5,000 at the end of year 1, $8,000 at the end of year 2, $10,000 at the end of year 3. So let's start off again by just seeing what the net income of the project is. And it does have a positive net income, so that's good. But does it have a positive present value? We'll have to check that against our threshold rate. And it says calculate the net present value if the required rate of return is 9%. I haven't done this yet, so I'm just guessing, but I'm skeptical that this project is going to actually return 9% in 3 years with a net income of only $5,700. But we will see. That's why we need to do the math. Okay, so now let's calculate the net present value. The net present value, you'll remember, equals NPV, and we start with the rate, which we indicated right there in C13, and then it's the values of the inflows only. So we'll run it C8 through C10, and then we're going to tack on the outflow, which will add because it's a negative number. It's the same as subtracting it. So we'll see that it has a net present value of 1751. So actually a little bit more impressive than I thought. That means the internal rate of return is going to beat 9%. Okay, so we can run the internal rate of return function, IRR equals IRR. And here's just all the values, the outflow and the inflows. And then guess, and I'll just use 9% for my starting point. I know it's going to be higher than that. And indeed, it works out to 14%. So internal rate of return beats the target rate, the threshold rate. It's got a positive net present value. So this project is a go. Okay, next up is problem 1027, which is a little bit more comprehensive application once again of net present value, internal rate of return. So we've got two projects here, and what I'm going to do is walk us through completing one of them. There's a lot of iterations that the question wants us to run. It looks intimidating, but it's not going to be too difficult because Excel is going to help us so quickly do the calculation. So hardest part of this is probably going to be to set it up. I've already created the template, so that's half the battle. So what we have here says Aluminum Building Products Company, ABPC, is considering investing in either of the two mutually exclusive projects described as follows. Project 1, buying a new set of roll-forming tools for its existing roll-forming line to introduce a new cladding product. After its introduction, the product will need to be promoted. This means the cash inflows from additional production will start sometime after and will gradually pick up. So we'll have low initial cash flows here, but then they will grow over time here. So not much payoff, and it was probably fail a payback test, wouldn't it? Not much payoff immediately, but growing payoff in the future, although that's going to be discounted more heavily the farther out in the future. So that's an interesting aspect of that project. Then project 2, modifying its existing roll forming line to increase productivity. Cash inflows from additional production will start immediately and will reduce over time as products move through their life cycle. So we'll get some immediate bang for our buck on that, but then it'll taper off. So less discounting, more early return. So it's going to be interesting to see which project wins out in the analysis. So let's go ahead and plug these values in for project 1, 200,000 outlay to acquire it, and then no payoff, so 0, 0 until year 3, where it's 20,000, and then it grows to 30,000 in year 4, 40 in year 5, 60 in year 6. Evidently, it's increasing growth rate, so they think they're going to get some market penetration here. And then 100,000 in year 7. So what's our total income from the project? Let's just auto sum that. It is positive, so that's a good starting point, but that doesn't guarantee that it has a net present value. That depends on our discount rate. So the initial discount rate, that says both of these projects have the same economic life of 8 years and average risk characteristics. ABPC's weighted average cost of capital, or hurdle rate, or discount rate. There's about half dozen different terms we can use for this. Threshold rate, hurdle rate, discount rate, required rate of return. All mean the same thing, and that always enters into the rate component of our calculations here. So there's our rate. Now, it says part A, which project would you recommend Mrs. Brown accept to maximize the value of the firm? Hence, calculate and compare NPVs. I'll do it for project 1. You can do the same procedure for project 2. Equals NPV of this rate and these inflows, and then subtract the initial outflow. I'm adding it because it's already a negative number. And let me expand my column so we can read that. Oh, it's got a negative NPV. And I'm not too surprised because the bulk of the income occurs out into the future where we are discounting it heavily. And it's not generating a 7% rate of return. So on the NPV decision, I'm going to say no. It's a no-go. Now, just to see what the IRR is, I'm expecting it to be lower than 7.2 because it doesn't have a positive net present value. So the IRR here equals IRR of that set of values. Now we put all the values in, remember, including the initial negative. And then the guess, I'll start at 5%, 0.05. And there we go. It's only 4%. So that project is a stinker, as we say. It doesn't meet the required return. So the IRR decision is going to agree. It's a big fat no. Now you can do the same thing for part A and B, calculate NPV and IRR. And then it says draw the NPV profiles of both projects. Now remember, the NPV profile is a graph of the NPVs at various discount rates. Well, in order to do that, we have to go ahead and calculate the NPV at these discount rates. So to make this easy, and I've just picked out some rates here, 0 through 20% at 2.5%, 250 basis point intervals. So the way I'm going to do this is name my range for my inflows. And let's call this P1 CF for cash flow, P1 CF. And I'm going to run NPV for this rate. With cell reference, I can fill this function down and it'll just drag down the rate over here as we fill down. And then the values are P1 CF. There's my range of values. And then we're going to subtract. Let's do this. Let's add that cell and let's lock that in because that's always going to be subtracted for each discount rate. So notice I put the dollar sign in front of the 7 to lock that, so that never moves. So we'll always be subtracting the 200,000. Okay, and hey, look, does that make sense? At 0% discount, at no discount, the net present value is just the net income of the project. Yeah, we're not discounting at all. The discount factor falls to 0 there, so that makes perfect sense. And then as we raise our discount rate, the net present value goes down, and that makes sense again because we're discounting by a larger and larger discount factor. So the higher the discount factor, the lower your net present value gets. And this one's going to cross the 0 threshold between 2.5 and 4%. Well, sure, we know that the rate that makes this net present value 0 is 3.97%. And so that occurs between here, so that all jives. So the only thing we need to do now to graph that is select the net present values, insert up here a 2D line graph. I'll do it with the points plotted. And let's name this Project 1 NPV profile. And I could leave it like that. That would work okay. But I should have here on the horizontal axis, I'm going to click on that and select data. And I'm going to edit the series. Oops, I'm actually going to I'm going to edit my horizontal axis labels to be the percents used for the discount rates here. And there we go. Now those show up as the proper percentages. And we could probably format this a little bit nicer by adding some grid lines to the vertical. There we go. I like that. Okay, so we could clean up the formatting here a little bit. In fact, I'm just going to rearrange that a little bit. I like my values for my horizontal labels to be on the lines, not between them, but that's just me. All right, so there's our net present value profile for project 1, and then you can follow the same procedure. You might need to back this video up and watch that again a couple times if you're not familiar with making graphs in Excel. It's very user-friendly though. You'll get the hang of it. You can do that for project 2, and then the final component of this question is to part C says what is the approximate discount rate at which both projects would have the same NPV? What is that NPV? You can take a stab at that and see if you can figure that out by looking at the graphs. One final thing it asks us in part D is, does the selection remain unaffected for 3 different weighted average cost of capital? Now, what that means is 3 different rate scenarios. So, and we'll label these 1 through 3. And the rates given are 5.4%. Whoops, I meant 5.4. 8.81 and 14.39. All right, well, what do we want to do? We want to run the NPV and IRR again for each scenario. So the rate is this one we just plugged in. My values are my project 1 cash flow range again. And then we're going to add C7, which was the initial outflow, to net it out. All right, so that makes sense. Anything above 3.97%, this thing's going to have a negative cash flow. And let's run the IRR as well. The values are, it's not project 1 cash flows, it's all of this. So I could name that range if I wanted to. Let's do that. Let's name the whole range, including the initial outlay, and let's call that project 1 P1 all. And then I can use that in my IRR function just to make things a little more efficient down here. So now I can do this equals IRR. Values is P1 all. And my guess is, I don't think I need one. There we go, 4%. Now to run that for the other scenarios, and I've mentioned this many times, this is what I love about Excel. All we have to do is copy, because I've set this up properly. And whoops, I want to copy just the NPV IRR component and paste that here. My cell reference will shift down. My NPV keeps rising at a higher discount rate. My IRR stays the same. Okay, copy it, paste it again here, and we see at 14.39% the NPV is even more negative, and the IRR is always going to be the same. All right, and then part E, we're basically doing one more iteration of this, one more repetition. Further market survey research indicates that both projects have lower than average risk, and hence the risk-adjusted discount rate should be 5%. What happens to the rankings of the projects using NPV and IRR as a selection criteria? Explain the conflict in ranking, if any. So I basically want to do this whole procedure again. I'm going to paste all of them in here, but now I'm going to change my rate to 5. And I don't know what it is for the other one, but you can run that and then see if there's any difference between NPV and IRR ranking versus the 2 projects. This one is going to be a no-go on the base of both NPV and IRR. This one, my sense is that it might depend on what discount rate we choose, so we're going to have to run all those options and then see what we get. Okay, now we're looking at a problem from our current textbook. This is a pretty straightforward NPV scenario, investment analysis scenario for a multinational company. So, copied the question from the book. It says, Delta Company, a U.S. MNC, is contemplating making a foreign capital expenditure in South Africa. The initial cost of the project is ZAR, which would be South African Rand, 10,000. The annual cash flows over the 5-year economic life of the project in South African Rand are estimated to be 3,000, 4,000, 5,000, 6,000, and 7,000 Rand. So I've got that set up down here in the table under cash flow projections. Year 0, initial expense, negative 10,000 Rand, and then 1 through 5, there's our cash flows coming in. Okay. So then it also gives us cost of capital, and parent firm's cost of capital in dollars is 9.5%. Long-run inflation is forecasted to be 3% per year in the United States and 7% in South Africa. Now, the reason that's important is because we're going to need to use something called the Fischer equation to work out an adjusted cost of capital based on the fact that the South African Rand is depreciating much faster than the US dollar. It's losing value at 7% per year, whereas the dollar is only losing value at 3% per year. So we're going to have to adjust the interest rate we're using, the discount rate we're using, to reflect the fact that there's a significantly higher inflation rate in the currency that we're using to invest for the investment project. So I've got some, if you're not familiar with the math on that, don't worry, I've got it spelled out here, and I'm going to show you exactly how to do it. Okay, so then we've also got the current spot foreign exchange rate, because we're going to have to translate the earnings, or we're going to have to translate the values back into US dollar terms. Okay, so it says the ZAR USD exchange rate is 3.75. So that would be in foreign terms. That would be South African Rand per 1 US dollar. If we want to think about those in American terms, of course, we'll have to take the reciprocal, divide that into 1. Determine the net present value for the project in US dollars by, okay, part A. So that's going to be right here, this international Fischer effect. Calculating the NPV and ZAR using the ZAR equivalent of cost of capital according to the Fischer effect, and then converting to US dollars at the current spot rate. Okay, so here is the equation for adjusting our cost of capital, our discount rate. It's called the international Fischer effect. Okay, and what this represents, it says the equivalent cost of capital, ECC, equals 1 plus the I sub D, the domestic interest rate, times the ratio of 1 plus the foreign inflation rate, that's pi sub F, over 1 plus the domestic inflation rate, that's pi sub D. So this is basically the inflation differential between the foreign and domestic currency. In this case, it's going to be larger than 1 because the foreign inflation rate is higher than the domestic inflation rate. So this is going to be larger than 1. So we're going to tack that on to 1 plus the domestic inflation rate, and then subtract 1 to work it out as just a singular interest rate. So what we're going to do here is we're basically going to add an inflation premium to this cost of capital. Now, that might sound familiar to you from a macro class. I hope it's familiar to some of you, because I'm sure some of you had me for macro or money in banking. We talked about just the original Fischer effect on the domestic interest rate. When inflation goes up, we have to add the inflation rate to the real interest rate to come up with the nominal interest rate. And this is pretty much the same thing. The math is a little bit different, but pretty much, you might look at this and say, what is just the basic inflation premium here? 3% per year inflation in the US and 7% in South Africa. So we've got a plus 4 percentage points or 400 basis points inflation rate in South Africa. So we're basically going to be adding that to the cost of capital, which is 9.5%. And let's do that math and demonstrate that. So we're going to run this math here in Excel. Equals 1 plus the domestic interest rate, I sub D, which is 9.5. So it's going to be 1.095 times the differential between the foreign and domestic inflation rate. So 1 plus the foreign rate, 1.07, it was 7%, divided by 1 plus the domestic inflation rate, so that's going to be 1.03. And then subtract 1, so 13.7, right? The raw prediction is 13.5, it's going to be pretty darn close. So that's our equivalent cost of capital for South African Rand, given that higher inflation rate. Okay, so what we'll do is we'll plug that in for our rate. I'll just say equals that cell. And then we'll run our regular NPV function on the cash flows in South African Rand. And then we'll take the NPV and bring it over, translate it into US dollars at the spot exchange rate. So this should be pretty familiar by now and pretty easy. So NPV, rate, comma, the set of values, only the inflows, close the parentheses, and then remember, subtract the initial cost of capital, which, because it's a negative here, it's got the parentheses on it, we're going to add it. Okay, so that gives us 6,384, and then we're going to convert that to US dollars at the spot exchange rate. So 6,384 Rand divided by the spot exchange rate, which, if I recall, was 3.75. Yeah, 3.75. You can see that's 3.75 Rand per dollar, so divide that by 3.75. And there we go, $1,702.49 is the net present value. Maybe this is actually like millions, right? So it'd be $1.7 million or something. Okay, let's run the IRR. That one's easy. All the values, remember all of them now, including the initial cash outflow, and then a rate estimate. I'll just go with 10% to get started. 0.10. Okay, 34%. Wow, that's a smoking rate of return. So what's the decision on that one? That's going to be a big fat go. It's much higher than the cost of capital. The IRR is much higher than the cost of capital. Net present value is positive. Okay, now let's move on to part B. It says converting all cash flows from ZAR to USD at purchasing power parity forecasted exchange rates, and then calculating the NPV at the dollar cost of capital. Okay, so how do we do the purchasing power parity conversion? Well, the math there is pretty simple. I didn't include it in a sidebar here, but I'll just write it down for us. So the way this math works is that we're just going to take the spot exchange rate, so let's call that ER sub S, times the ratio of currency 1's inflation rate, let's call that currency 1 pi, divided by currency 2 inflation rate. Now, the reason I haven't specified which currency goes on top and which currency on bottom is because it matters if we have this in American terms or foreign terms. Whichever terms we have it in here, that's the currency we want on the top of the ratio here. So the ratio of whatever currency we're dealing in, its inflation rate divided by the other currency's inflation rate. So what that's going to look like for us, I want to put this in American terms because we're bringing stuff back to dollars, so we might as well start with that. So what is the spot exchange rate from the rand to the dollar in American terms? Well, I know that it's ZAR to USD is 3.75 to 1, so that means $1 is 3.75 rand. To get the number of dollars per rand, we have to find the reciprocal of that, right? So it's going to be 1 divided by 3.75. Okay, so the spot rate in American terms is 27 cents, $0.27 per rand. So when I do now, in these cells down here, I'm going to run the purchasing power parity math. So I'm going to take the spot exchange rate in dollar terms. By the way, I'm going to lock that in because I forgot to mention something down here. We'll come back to this. That we're taking the currency because we're dealing with compounding of this ratio of inflation rates over time, over several years out. We're taking this, we're compounding it, so to the power of n being the number of years, which we'll just use the values over here. So same thing for currency 2 to the power of n. Okay, so now we're ready to actually run that math. So we'll take the spot exchange rate in American terms, lock the reference there, and then times the ratio of the currency 1 inflation rate plus 1 technically, so it's going to be 1.03 because the US inflation rate was 3%, right? To the power of 0 divided by the foreign inflation rate plus 1, which is going to be 1.07. South Africa's inflation rate was 7%, to the power of 0. Now, of course, anything to the power of 0, you'll probably recall, is 1. So this is just going to be times 1. It's going to be the spot exchange rate, which makes sense because this is today, right? Year 0 means no time has elapsed, so we would use the spot exchange rate. But as we fill this and apply it forward in time, now we'll see, and for example, so click on year 5, we're taking everything to that power. We're taking it to the power of 5 there, C24. And that's compounding these, and so it's going to create a ratio effect that's less than 1, and that means the number of dollars it takes to buy a South African rand is going down. What does that mean? That means the dollar is appreciating versus the rand. It used to cost me 27 cents to get a South African rand. Now it only costs me 22 cents, well, 5 years out. So that means the dollar's going up and the rand is going down. So that makes sense given that we know that the rand inflation rate was higher than the dollar. Okay, so there's our purchasing power parity future exchange rates. Now all we need to do is bring the cash flows over at those exchange rates. So the initial cash flow, that exists back here in the cash flow projections. So times those by the PPP exchange rates, and then fill. And there we go. Now we've converted our cash flows from South African rand into dollars at the projected exchange rates based on purchasing power parity. Okay, almost done here. Now, what's the cost of capital we're going to use to discount this? We're going to use the dollar cost of capital. The parent firm's cost of capital in dollars is 9.5%. So let's plug that in. And then remember, running the NPV function is very easy. That's the easy part of this actually. Setting up and converting the values is the tedious part. But we're ready to do the easy part. So equals NPV rate right there, 9.5. Remember, only the cash inflow values get discounted here, so that's H20 through 24. Close the parentheses, and then we are going to add, because it's a negative, it's subtracting the initial outlay after we've done the NPV. And there it is. Okay, 1702.49. Wow, that's exactly the same as what we got using the other method. Discounting the cash flow in South African rand, and then bringing it over, having adjusted the cost of capital per the inflation premium, the Fischer effect. So different math, same result. And then let's run the IRR again, of course. There's the value, all the values now, including the initial negative outlay. And then I guess I'm going to go with 10% again. 29%. This IRR is a little bit lower, but still pretty large, still looking good. So this is definitely going to be a go as well. So no matter how we slice it, got exactly the same net present value. We got pretty close, actually. IRRs way above the threshold cost in either sense, and so the project is a go. So part C says, are the $2 values NPVs different or the same? They're the same. I'm not going to make you explain this in a text box or anything, but just be aware of the fact that the reason they're the same is because we are essentially doing the same math here. We're just using a slightly different transformation method. Here we're doing the transformation of the currency up front. Here we're doing it after the fact, right? Here we found the value in South African rand. By the way, that shouldn't have a dollar sign because that's not dollars. Okay, this one is though. So we did the present value of the project in the local currency, then we converted it to dollars. Here we use the purchasing power parity math to convert the exchange rate, and then we took the cash flows into dollars and then discounted them. We got the same results. Okay, kind of tedious math on international finance is that's subtitle, lots of tedious math. Finally, it says in part D, what is the NPV in dollars if the actual pattern of South African rand dollar exchange rates is as follows? Year 1, 3.75, or starting point 3.75, year 1, 5.7, year 2, 6.7, and so on. So I went ahead and just typed those in for us, and then what we'll do is adjust the cash flows at those exchange rates. Okay, and so this is South African rand, and this is South African rand per dollar. So what we want to do here is take the initial cash flow amount in South African rand and divide it by this foreign terms exchange rate. Okay, and let's fill that down, and then because we've already converted them to dollars, we're going to use the dollar interest rate, the cost of capital. Now, I have a feeling that this net present value is going to be quite a bit lower because look at these dollar converted cash flows versus these. And I know here that the rand is losing tremendous value here, especially just in year 1. It goes from 3.75 rand per dollar to 5.7. It takes a lot more rand to buy a dollar. The rand is losing value like mad here, which means we're getting a lot less cash flow once we convert back to dollars. In the final year here, it's only 800 instead of 1,500. So I have a feeling we're going to have a much smaller net present value. Let's run it and see how much smaller. There's the rate. And then there's the positive cash flows, close the parentheses, add that initial outlay. And whoa, it's negative. Wow. Okay, so not only is it smaller, it's actually negative. In other words, we're not going to recoup through this series of positive cash flows the initial investment of negative 2666. So this is definitely a loser. Before we say anything else, let's put a big no in there for the decision. And then let's run the IRR. Of course, the IRR is going to be less than 9.5%. If this thing's a money loser, we're going to spend 9.5% for the capital and then earn less than that on the investment. So that's what makes the NPV negative, and that means the IRR is going to be less than the threshold rate or the opportunity cost. Let's all put in a guess in here, 5% to start Excel off. And it's 8%. Okay. So there you go. There is a fully worked out present value situation that incorporates that foreign currency analysis. I hope you understood that. I hope that's clear. I hope this is like a nice addition to some capital budgeting knowledge that you might have already had maybe from a finance class. If you haven't taken finance yet, you'll be using this kind of thing, and it'll probably feel easier once you get over to domestic finance where you don't have to do the foreign currency gymnastics. But we're starting to kind of get into the realm of what financial analysts actually do. So if you enjoy this kind of stuff, keep learning it and sign yourself up for a finance major and become an analyst and make a lot of money doing pretty tricky math, but knowing conceptually what you're doing. Actually get Excel to do the math for you, and it's not too bad, and you can do quite well for yourself helping businesses make these very important decisions. Okay, so that's all for now. Homework 4.5. Email me if you have any questions, need any help. See you next time.